Good morning. So let's begin. So in the last lecture, we were looking at, or we finished reviewing the three modes of heat transfer. What I want to begin today is some formal analysis of heat conduction. But before we do that, one fundamental law that we will use now very frequently would be the law of conservation of energy. And so I thought that I'll just remind you that in heat transfer, we will typically formulate this first law on a rate basis. Okay, so and when you apply on a rate basis, we will typically formulate the law applied to a control volume. So basically, we will use an Eulerian method rather than the Lagrangian scope to define the conservation of energy. So basically, what it requires is that we have to identify some kind of a control volume where some kind of flow is taking place. So let's say this is control volume. We have in this control volume we will typically have some rate at which energy comes in. We may have some rate at which energy goes out. And in this control volume, so now remember one thing, that when we talk about the control volume approach, we always have the control volume, but we also have an associated control surface, because this is a closed control volume. So let me define a closed control surface, which is which sort of encapsulates this control volume. So any energy and matter, or transfer of material, that would mean matter, would actually happen across this control surface. But there would be other aspects related to this control volume which we also need to account for. These could be, for instance, in the form of heat generation. So internally, some processes could be taking place, maybe some chemical reactions, or this is the case of a nuclear reactor. Let's say, in which case heat could be actually could be generated by unit volume. And then, of course, what we are looking for is the rate at which energy is being stored in this control volume. So the rate at which maybe temperature changes in this control volume. So the first law, in the most basic way, for this problem would be that the rate at which energy comes in minus the rate at which energy goes out plus the rate at which energy is generated would be the rate at which energy is stored. Okay, so we are now looking at, for this control volume, as I said, we are doing it on a rate basis. We are looking at how maybe internally, pass with unit with passage of time, how energy is getting accumulated in this control volume. So this is the accumulation, and as I said, this is the generation. And it need not be always generation, by the way. Our sign convention allows us to say that even if energy is being consumed, so for instance you have an endothermic chemical reaction, in which case energy is actually going to be consumed, so that would become negative in that way. Now what this brings out are two scenarios, if I because these will be scenarios that we will be using very frequently now in heat transfer. The first scenario that we will be dealing with is a case where, let's say, E dot in minus E dot out, or rather, I should not say minus E dot out here, but E dot in plus E dot generation is more than E dot out. If that was the case, it clearly is a scenario where energy will be accumulated in the CV. So this will lead to accumulation, and in most problems that we will do, this will actually lead to a rise in temperature within the material. And the second special case that we will tackle would be one in which E dot n plus E dot g is equal to E dot out for all times, which will basically be a steady state case. So these will be two scenarios that we will deal with very frequently from now on. The other thing that you should now remember, because I'm just going to say this now, and you've done this in fluid mechanics, by the way, but I should just reiterate that, see, exchange of matter or energy happens, as I said, across a controlled surface. So it is what we call as a surface phenomena. But these generation and storage terms are essentially associated with volumetric descriptions. So generation and storage will actually be volumetric phenomena. So they will affect the whole volume, and so they are essentially proportional to the volume of the CV, and the rate at which energy comes in or goes out would actually be dependent on the surface area of the of this control volume. So keep this in mind, because I want to use this now to show you one fundamental aspect of how to apply boundary conditions in any heat transfer problem, and this is again based on conservation of energy. So let's just look at energy conservation, let's say, or energy balance on a surface. And by a surface, I basically mean an interface between a fluid and a solid. So the problem could be imagined like this. Say you have a surface, okay, which is a solid on one side. It is next to a fluid. So let me define that the fluid has some heat transfer coefficient H, maybe some temperature T infinity, which is not the same as the temperature of the solid. And just to make it more general, let's also say that far away we have some surroundings, so that we can also account for radiation effects. So let's say the surroundings are at some temperature T surroundings. Let me not use double R here. TSUR is more than enough. Okay, so that there could be radiation exchange between the solid and the surroundings. Okay, now what we can do is, if I have to look at how energy goes, let's say for now, so the solid is at a higher temperature as compared to the fluid in the surroundings. So I want to know how energy transfer occurs from the solid to the surroundings or the fluid. Okay, so there are three modes that I can identify. I know that energy must be going through, let's say, the conduction mode, and I'm going to say Q double dash to denote is that it has a flux for now. So energy is coming to the solid surface in the form of conduction, but at the surface it goes away in the form of convection. And pardon me for writing it very small here, but convection, or it could go in the form of radiation. Okay, so we will apply energy balance at the interface of the solid and the surroundings, or the fluid. By what we'll do is, we'll have a control volume which has, I'm exaggerating it here, but let's say which has a very, or which has an infinitesimal thickness. So let's say this is my control volume, or this is the, rather I should say, these are the control surfaces now of the control volume. So these are the control surfaces. Okay, so say that the thickness is delta x, let's say, and let me say the surface area. We are taking it as a plane surface for now. Let's say the area is A, although this won't matter. So what I know from energy conservation is that if I apply this equation, which is E dot in minus E dot out plus E dot G is E dot ST. Let's say there is no generation here on the surface, or even if it's there, it doesn't matter. So we can say what is coming into this control volume. It would be Q double dash conduction times the area. That is the amount of energy coming in. What is going out? That would be, let's say, minus Q double dash radiation times A, plus, let's say, Q double dash convection times A. Because remember, this is a flux. Flux times area will basically be the rate of heat transfer, or the rate of energy transfer. Plus, we need to have the generation term. So let's say E dot G is the rate at which energy is being generated per unit volume. So I can write E dot G into A times delta X to be the rate at which energy is being generated in this infinitesimal control volume. Okay, and what is going out is, as I said, is E dot storage. So let's say this is also E dot storage, which is the rate at which energy gets stored in the control volume, or rather energy gets stored per unit control volume times again A times delta X. Okay, so I can get rid of the areas quite easily. Okay, and now what I'm going to do is I'm going to say that the control volume I'm going to shrink it. So in the limit delta x goes to 0, so we are shrinking the control volume. What we will get is that these two terms, this and this, they are going to be 0. And so what we'll be left with is q double dash conduction minus q double dash radiation minus q double dash convection is 0. And that basically becomes sort of the boundary condition for our heat transfer analysis. So this will be the form of the boundary condition that we will use in almost all our heat transfer analysis. Now, what we will see, I mean, what we may, the kind of problems that we will see would be that sometimes radiation will not be there. And so we'll only have conduction flux converting into convective flux. And sometimes the convective flux will not be there. When we go into detailed study of radiation, we will ignore convection. We will assume that the surroundings are vacuum, in which case convection will go to 0. So all conductive flux will actually convert into radiative flux. But do remember that it is not a conservation of fluxes, it is actually a conservation of energy, because this, what I've applied here, is actually true when you are looking at, or rather, it's true when you have any surface. It could be circular surface or spherical surface, but we have applied it over a small element there. So let's move on with these tools now, which I have described. One is conservation of energy. Second is how to apply boundary condition at the interface of a solid and a fluid, or maybe even with surroundings which are at some other temperature as compared to the solid. And again, by the way, one more thing, I have been sort of little casual. I've so far not described anything to do with the coordinate system or even the direction in which things are being assumed to be positive. I've just taken some of my own convention that conduction flux is coming in a certain way, convective flux is going in some other way. It need not be this. I mean, it all depends on temperatures. So we'll see that it could actually be the other way around as well. It need not necessarily be this, that that all, irrespective, even if the surface is at a lower temperature, definitely you cannot have conductive flux converting into convective flux. It would rather be the other way around, that the hotter fluid would actually cool the surface, or would rather heat the surface, so you will have heat transfer from the fluid to the solid. But we'll tackle those as we go along, and I hope that the sign convention will start becoming clearer along this way. So let's look
Excuse
at,
me, sir.
yeah.
Sir, how did we arrive to this? That while you were writing this storage energy and the generation energy, how did we calculate the volume of that small area, small control volume?
Okay, so what I said was, so did you see this? Can you see the sketch, right?
Yes, sir. Yes.
So I said that let's take area is A is the area of the slab, let's say of that plane interface. Hmm? Delta X
We
has
are
been taken
we are considering it as a shape of a cuboid. Then
as a,
cuboid.
yes. I mean, this is, so you can think of it this way, that A is the area into the plane of the paper,
Okay.
and delta X is the thickness.
So we are basically taking the cuboidal
Yes, so
shape
it's
for
a
this.
cuboid. It's a cuboid which has an area of, let's say, two faces to be A, but one length is delta X.
Okay, sir. Hmm.
Okay,
Yes.
because what I'm saying is that would be the control volume. So the control volume here, let me choose some other color. So the control volume was this control volume. If that is clear, I don't know.
Okay, sir.
Okay, So we are taking a control volume which is very close to the surface, has a very small thickness, but it goes all the way down into the plane of the paper. Okay.
Yes, sir.
Okay, so let's go to conduction now. So remember, we spoke about conduction as a transport of energy because of some random motion, random molecular activity, which primarily happens because of the presence of a temperature difference. And what I wrote in the earlier part was that conduction or rate of conduction is basically given by Fourier's law, which is actually a phenomenological model. Phenomenological model, which basically means that it is actually developed from what we observe. Okay, it is not, it's a law, but it's based on observations, and it is based on experimental evidence that this actually holds, and it applies to all states of matter. Now, the way Fourier's law was originally described was that, let's say you have maybe a medium which has two surfaces at different temperature, let's say T1 and T2. Okay, and let's say the medium has some, I'm drawing it almost like a parallel plate capacitor, but anyway, so let's say the medium has some area, cross section area A. So I have described delta T here as T1 minus T2, assuming T1 is more than T2. So what is observed is that the rate at which energy transfer happens from one phase to another, Q, why am I writing? It's not a Q vector right now, it's just Q, but saying that it goes from, let's say, left to right. So Q was found to be proportional to the area of cross section, to the temperature difference, but inversely proportional to the thickness or the distance between the two surfaces. And so we could write that Q is some Ka delta T delta X, where K becomes the constant of proportionality, and we call K to be the thermal conductivity of the medium. Now, this is of course meant for, you know, a system here which in which we have not considered anything else taking place, and you've just described this based on, some observed phenomena. But the problem is not that simple. In fact, in the limit that delta x goes to 0, we get a better description of Fourier's law, where we can now write the flux, not the flux, rather. Let me say heat transfer rate only. So if I define x direction like this, so Qx is minus Ka dt dx, where we have the same description as earlier, except I have brought in a negative sign to account for the fact that the energy transfer will happen from a higher to a lower temperature. So dt dx will always be negative as we go in the direction of heat transfer. So a negative sign ensures that we are saying that the heat transfer rate is positive. And this also allows us to write flux as minus k dt dx. Now, flux actually, although heat transfer rate is a scalar, flux is not a scalar. Flux is actually a vectorial, is a directional quantity. It has a direction, so it's a vector. In fact, the generalized form of Fourier's law writes it in a vector form. So we can write the flux vector q double dash vector is minus k times gradient of temperature, where you know what the gradient operator is. So this means we can write this as minus k, let's say I cap dt dx plus j cap dt dy plus k cap dt dz. So the flux is a vectorial quantity, and the idea that it depends on gradient of t it actually, what it means mathematically, and this you may recall from, I don't know, MA, I don't know what the numbering now is, but some one of the earlier, I think the first year in the first semester course on mathematics where you must have done differential equations. So you may recall that, let's say I have a surface, or not a surface, a line along which I can say temperature does not change. So let's say this is an isotherm. So temperature is constant along this line. So what it means is that operating, when you have a del operator on top of the temperature, and this is what is giving us a flux, it basically means that the heat flux is actually normal to this line at each and every point. So we'll have heat flux vector pointing in this manner. So everywhere, I should say, it would be perpendicular to this line. So once we have information, and this technique helps, is very helpful in heat transfer. So if we can identify a line of constant temperature, we already from there itself we know what would be the line of direction of heat transfer. Okay, by conduction, that it would be normal to that line of constant temperature. So knowing this, we can also write. I mean, if once the way we've written flux as a vector, we can also decompose into the components. So for instance, I can write flux as q double dash x I cap plus q double dash y j cap plus q double dash z k cap, and which basically means that q double dash x is minus k, and now I should actually write partial derivatives and not, so dt dx, q double dash y is minus k dt dy, and q double dash z is minus k dt dz. So we will resolve our flux into three components, and basically one component itself in it, in entirety cannot tell us which way the rate, which way the heat is traveling, or which way the heat transfer takes place. We need all three components. But in this course we will actually tackle problems where we would only concern ourselves with one, at maximum two dimensions. We will not go to all three dimensional heat transfer. That is for an advanced course, and not out of, not in the scope of this treatment. Okay, now in general we can write, in general, that the thermal conductivity of a solid is more than the thermal conductivity of a liquid, which is more than the thermal conductivity of a gas. And the simplest example I can give you is that, let's say K of copper, which is one of the best thermal conductors, is roughly 390 watt per meter Kelvin. K of water is roughly 0.61 watt per meter Kelvin, and K of, let's say, carbon dioxide, which is a gas, is about 0.016 watt per meter Kelvin. So the thermal conductivities will progressively go down, and again that's because of differences in the intermolecular spacing between these phases. So thermal conductivity will be one important parameter for all conduction analysis. The second important thermophysical parameter that will come out, or that we will require, or we will actually encounter very commonly, is what is called as the ratio of the thermal conductivity and the volumetric heat capacity. So we'll call this as alpha, this property, which is the thermal diffusivity. So alpha is being defined as K which is the thermal conductivity, to the volumetric heat capacity, that would mean it's not the mass capacity, specific mass capacity, but the volumetric capacity. That would mean it would be rho times Cp. So in terms of units, we know that thermal conductivity has units of watt per meter Kelvin, density is kilogram per meter cube, and heat capacity will be joule per kilogram Kelvin. So the units now, if you work out, so kilogram goes here. Watt is basically joules per second. So Kelvin also cancels. Joule will cancel, and meter cube is here, and there's a meter. So we'll be left with meter square per second. So the units of thermal diffusivity will be meter square per second. And we call it diffusivity because it's very similar to the momentum diffusivity. Does anybody know what momentum diffusivity is? Having done an entire course on fluid mechanics, what is momentum diffusivity? Does anybody know? Or what do we call as momentum diffusivity? Any idea?
Uh, is it like a measure of how well the momentum is like um, basically how it is spread between the particles, like a measure of like
No, but
inflow?
what property is used to define momentum diffusivity? Can you name a property? Okay. So momentum diffusivity is,
Viscosity by
Viscosity.
so
so yeah, it's a kinematic viscosity, which also has units of meter square per second. So momentum diffusivity is new. And as I said, alpha is similar to momentum diffusivity. The role momentum diffusivity plays in transfer of momentum, the same role alpha plays in terms of transfer of energy or transfer of heat by conduction. Okay, so alpha basically denotes in a rough sense. Okay, it is the ability of a material. So it's ability of a material to conduct thermal energy, because remember it's K by rho Cp. So to conduct thermal energy versus or relative to storing thermal energy. If we have a material which has a high alpha, it basically means that the material, instead of storing, is actually converting that into conductive, into transport by conduction. But if we have a material which has a low alpha, it basically means that the change in temperature, or the change in internal energy of the substance is higher relative to it, giving away that energy. Okay, so we will use this property alpha along with K very frequently from now on. And the way we will use it is something that I want to show now. So let's pose a problem, okay, and then we'll start our formal analysis of conduction. Let's say I give you a material, some material. It could be solid or liquid or gas, doesn't matter. Let's just say, for the purpose of making it a simple discussion, let's say I give you a solid. I tell you that internally the solid has, or rather, let's say the solid is experiences some temperature gradient, in a three-dimensional sense. Let's not worry about 1D only. So in a three-dimensional sense, that solid experiences some temperature gradient. And let's say that internally there is also some chemical reaction or some rate of heat generation. Maybe there's a current collector, there's a current carrying conductor in the solid, or the solid itself is a current carrying conductor, because of which there is some ohmic heating. So given all these conditions, and I ask you that, can you calculate the rate at which temperature will change in this solid? So the heat, or the energy conservation equation, is the tool that we will use to describe this, or to be able to predict how the temperature will change. But more importantly, it is some kind of a differential analysis that we will use from now on. So we'll use conservation, but on a differential sense, like the way you did in fluid mechanics. If you recall, we can write conservation in both integral and differential ways. So I will actually take the differential part from now on in this course, where we will write conservation laws in differential format. Both are the same essentially, but differential will help us to write it on a local basis, on a per or on a, for each and every point. So to determine, let's say, temperature in a medium, or temperature distribution, I should say, we will apply conservation of energy, and let's say the medium happens to be, just for the sake of this argument, some kind of a three-dimensional body which looks like a cuboid. Need not be. Okay, the first important thing would for me is to do here is to define the coordinate system. So I will define x, y, and z. So a right-handed coordinate system. uh, let's say that this medium is a homogeneous material, so the properties are the same everywhere. Let me also say that there is no bulk motion. If it's a fluid or a gas, it's a fluid, so no bulk motion. If it's a fluid, then there could be bulk motion, which means there could be flow. Let's assume that there is no bulk motion. If it's a solid, we don't have any problem. The third thing that I will assume is that I will develop this conservation equation in Cartesian coordinates. Later, I will also discuss how we can work out this conservation law for other coordinate systems, mainly cylindrical and spherical coordinates. Okay, so what I'll do is I will take a differential control volume in this substance. Okay, so this is a differential control volume, and I will try and apply conservation principles to this differential control volume. This is very similar to any continuum mechanics course that you do, solid mechanics or fluid mechanics. We always start with the differential control volume. Okay, and then I will try and address this problem, that what should be t x y z t. What should be the equation that governs this distribution, both in time and in space. Okay, not just, we're not just dealing with steady state systems. So how would it change with time and space? So to start with, let's say that I'll blow up this differential control volume to make it easier to understand what we are going to apply, or what conservation principles we are going to apply. So let's say our control volume, the differential control volume, looked like this. So this was a differential control volume. uh, I will label a few faces because I would need that to explain to you how things are working. So let's say A, B, C, D, E, F, G, H. Now remember the coordinate system that I have used. So I'm going to say that the faces have certain lengths. So this face has a length dx. This has a face dy, and let's say this has a length dz. Okay. Now let's apply conservation of energy to this control volume. Now to do it, I will do it in the most simple form first, and then we'll invoke the Fourier's law. So say that there is, on this face, which is ABCD, let's say we have QX amount of heat transfer by convection or by conduction. So let's say from the other side, maybe a differential control volume next to this control volume, we had QX coming in to the face ABCD. Let's say we have Q, not QY, this should be Qy should be here, sorry. So Qy coming on this face, and let's say Qz coming to the bottom face. So what it means is Qx is the conduction heat transfer rate, which is perpendicular to the face A, B, C, D. So Qx is conduction heat transfer rate perpendicular to A, B, C, D. Qy will become conduction heat transfer rate, which is perpendicular to, this will be A, E, HD phase. And these are the control phases for this control volume now. And Qz will be conduction heat transfer rate, which is perpendicular to, this will be CDHG. So let's say these are the three heat transfer rates into these control phases. Correspondingly, because we are moving, we're doing a differential analysis, I can say that on the phase EFGH, which you can hopefully see on the screen, and maybe let me make it a little smaller so that you can see the entire sketch. So on the phase EFGH, let's say we have heat transfer going out, which is Q at x plus dx. Similarly, if heat transfer going from the back face, which would be Q y plus dy, and heat transfer going out from the top face, which is maybe Q z plus dz. Okay. To make the problem a little general, let's also say that this homogeneous medium also had a rate of heat generation, which I'm going to write as Q dot. So Q dot is the rate of heat generation, which is on a volumetric basis. Okay, so this is per unit volume. So the units of Q dot will be sort of like watt per meter cube. So per unit volume, this is how the rate at which energy is being generated or consumed in this control volume. And Q dot itself may be space dependent, so there's no issue with that. Okay, space or time dependent, so we're not very worried about that. So these are the things taking place in this differential control volume. So we can now apply, uh, or before I apply conservation, let me also write one more aspect now, that when we write Q going out, which is Qx plus dx, Qy plus dy, and Qz plus dz, the reason we are writing it in this way is that we're saying that it's an infinitesimally small control volume. So Qx plus dx could be expanded in a Taylor series about the location x. So we could write this as Qx plus dqx dx times dx plus higher order terms, which would be second, order delta x dx square, dx cube, and so on and so forth, except that we are working with differential systems, so these would be neglected. So we will linearize, as we do very often in calculus, we'll linearize to the first derivative only. Similarly, Qy plus dy would be Qy plus dqy dy dy plus higher order terms, which I'm again going to neglect, and Qz plus dz would be Qz dqz dz times dz plus higher order terms, again being neglected. Okay, so we've linearized, and now we can apply conservation to this control volume. So let's apply conservation. So remember, the conservation law said E dot in minus E dot out plus E dot generation is E dot storage. Now, what would be each and
Sir,
every term? Yeah,
sir, can't QX depend on Y and Z as well?
can't what depend on Y and Z?
QX.
No, because in this case, if you see the convention that I'm taking, so it is Qx is actually right now the way I've written, right? It can depend on those, but we're trying to see, think of it this way, that Qx is actually going along, or it's perpendicular to the face, or it's perpendicular to the face which has a normal along the x direction. So I'm expanding it only along that direction. Or heat transfer in my case is taking place only along this direction.
But sir, if we look at different points in the solid, then
Hmm.
on the same surface, won't QX vary from one Y coordinate to another and
True,
Z
but if you
coordinate
think
to
of it
another?
this way, see, Qx plus dx, are we, I mean, what is changing from Qx to Qx plus dx? Which spatial coordinate is changing?
X.
Yes. So I'm expanding along x only then, right? Because other dependencies will actually go to zero then,
Okay, okay.
right?
Yes.
Okay. So let's move on. So by the way, so what I was saying is that once we have this uh, energy conservation equation, we need to also look at what would be E dot G and E dot ST. Okay, the storage term. So what would be E dot G? Remember, we wrote that Q dot is the rate at which energy is being generated in this per unit volume. So Q dot times the differential volume should actually give me the rate at which energy is being generated. Similarly, storage term, assuming there is no phase change, that is a key assumption here. Okay, assuming there is no phase change, the storage term will only correspond to change in temperature. So I can write this as, let's say, rho into dV, which will become, the mass, into specific heat, into the rate of change of temperature. So sort of like mcp delta T, which we use in thermodynamics. So these two terms will come out like this, except dV is the volume of the differential element, which would be dx dy dz. So I will use this now to calculate what would be the overall energy balance. So let's write E dot in. So E dot in this case is Qx. So basically all energy that is coming in. So energy that is coming in is Qx plus Qy plus Qz. Energy that is leaving out would be Qx plus dqx dx, and I can maybe say plus Qy plus dqy dy plus, is it visible? Yeah, Qz plus dqz dz dz. So that is the amount of energy going out, plus storage, which would be q dot, let me say, dx dy dz, is what is being, that was the generation term, and what is being stored, that would be rho dx dy dz, cp dt dt. Okay, so we'll have, in this case now, some terms will disappear. Qx cancels here, Qi will cancel here, Qz cancels there. So what we will be left with is minus not Qx, minus, I can say, dqx dx just dqy dy dy plus dqz dz dz plus q dot dx dy dz is rho dx dy dz cp dt dt. So now let's apply the Fourier's law to define what qx, qy, and qz were. So recall that qx, which is the rate of heat transfer along the x direction, this should be in from Fourier's law. This should be minus k times. If I can write, because these are small areas, I can say this is dA, and let me write dt dx, except what dA am I referring to? So for this I need to go back to the sketch. Okay, so let me just bring you here. So what area am I looking at? I'm looking at this area ABCD, which has a normal along the x direction. So I'm going to write this as minus k dax dt dx. Okay, to define that this is the area along the x direction, and that area has a definite value. The value is, it has dimensions of dy dz, right? That is the area of that face. So this could be written as minus k dy dz dt dx. So clearly dqx dx would be d by dx of minus k dy dz dt dx, which I can write as minus d by dx of k dt dx dy dz, since the elements in the other directions are not dependent on the x coordinate. And now what I've done is I've taken the thermal conductivity to be, even though I'm saying the material is homogeneous, the conductivity itself may actually be depending on, space, and or depending on temperature. So I've taken it inside the derivative. I've not pulled it out. For a case of constant thermal conductivity, we will actually pull out the thermal conductivity later, but not yet. Though in the general system, K may actually be space dependent, right? You can have, as I said, you can have composite slabs, in which case again thermal conductivity changes with space. Similarly, we can write Qy, which would be minus K. Again, we need an area dA dt dy, and which area will that be now? So if we go back here, Qy is coming into this phase, which is A E H D. So this is the phase in which heat Qy comes in, and the dimensions of that phase are dx into dz. So I can write this as dy. So this being minus k dx, sorry, dz dt dy. So dqy dy would be minus d dy of k dt dy dx dz. And finally qz would be minus k. I can now write the area clearly. It would be dx dy dt dz, which implies dqz dz would be minus d by dz of k dt dz dx dy. So The whole purpose of doing this was actually to assemble these expressions. So one, there is a second one here, and the third one is actually here. If I can maybe bypass some things and say that this is something like this. So once we have these three uh, derivatives of the heat transfer rate, I can now plug them in into this equation. And let's do that, okay, to complete this this formulation. So what we will now have is, so remember there was a negative sign now. So I'm going to just quickly jump over now in one step. There's a negative sign here, and then there's a negative sign in front of every of these quantities. So I'm just going to write this as positive. I'm not even going to bother writing negative negative, so this will become d by dx of k dt dx, and the multiplication is dy dz, except if you look at here, dqx dx is also multiplied by dx. So this will also have a dx, plus we'll have a d by dy of k dt dy, and this will have dx dz, but it would also have a dy if you check from the earlier step, and then d by dz of k dt dz dx dy dz, plus the the generation term. The generation term is q dot dx dy dz. This should be equal to this storage terms. This is rho cp dx dy dz dt dt. And now I can safely get rid of this common factor, and what we are left with is the equation that we need to describe the temperature distribution in this medium. So we have d by dx of k dt dx plus d by dy of k dt dy plus d by dz of k dt dz plus q dot is rho cp dt dt, and that is the heat diffusion equation that we will very commonly use from now on. So that will become our fundamental tool for analyzing almost every heat conduction problem from now on, except of course this equation is written in Cartesian coordinates. I will show you in the next lecture how to write this in the other, as I said, cylindrical and spherical coordinates, because many problems also involve heat transfer in cylindrical and spherical systems. Okay. Now, one of the key aspects that you should not forget, even though the equation is now in differential terms, is that this is actually a statement of the conservation of energy, and more importantly, each and every term in this equation actually has a significance. It's there for a reason. Even if you may not be mathematically oriented and may not want to say it explicitly that what each and every term may represent, but there's a way of describing the essence of this equation by just very pure basic calculus. Now, the way I want to explain this to you is that, so if you look at this expression, let's say flux of x minus flux at x plus dx. Let's say we want to explain what this should be. So in Fourier's law, flux is minus k dt dx, and I can write flux at x plus dx to be minus k dt dx minus d by dx of k dt dx dx. So what it means is, if you see this now, these two terms cancel. So what we end up getting is d by dx of k dt dx dx. So in a way, what I'm trying to say is that in a nutshell, the first term here in this equation, it sort of represents a net conduction heat flux. This first term, it sort of represents a net conduction heat flux into the control volume, but in the x direction. Similarly, the second term would represent the net conduction heat flux into the control volume, but in the y direction. The third derivative here would represent the net conduction heat flux in the z direction into this differential control volume. So what it's saying is the net, and by the way, I'm saying net here. Okay, this is the net conduction heat flux, which is into the differential CV and which is in the x direction. So net is the main word here, that we're dealing with net heat flux. And it's almost like, if you remember, that the Reynolds transport theorem, we have this efflux term, right, which is sort of like, how much net things are going out. In this case, we're dealing with how much things coming in. So remember the first law, though it may not, there are different conventions of writing the first law. Some people say that heat going out of the system is positive, some say heat coming into the system is positive. I'm using a system which is more traditional, which says heat coming into the system is positive. So we are saying that the net heat flux coming into the system is being taken. So that net heat flux plus the rate at which energy is being generated in the control volume is what is leading to a change in temperature of the control volume. So thermal energy changes. In our case, the interpretation is that it is net heat flux coming in plus rate of any heat generation is what is leading to change of thermal energy in this system. So that is a physical interpretation, or I would say another interpretation of this heat diffusion equation. Okay, so let me take a few simple cases for today before I think, yeah, we will close the class and maybe have a short discussion about the tutorial today. So let's just take a few simplified versions of this equation. The first most simplified version is, let me say if conductivity was a constant. If thermal conductivity was a constant, we can see that it will actually be pulled out from all the derivatives, and then I can write d2t dx square plus d2t dy square plus d2t dz square plus q dot by k would be rho cp by k dt dt, which can also be written as 1 by alpha dt dt. So here we see why alpha is important. So alpha basically becomes one of those fundamental properties that governs the response, or that governs the solution of this equation. Okay, so that is one simplified version. The second one is, let's say if we are dealing with steady state. So under steady state, dt dt would be 0. Temperatures will be time invariant. They won't change with time. And so we will have d by dx of k dt dx plus d by dy of k dt dy plus d by dz of k dt dz plus q dot is 0. The last simplified form, which we will actually use most commonly in this course, is when we can say that heat conduction is only in one dimension, which would basically mean that changes along the other two directions are negligible. So if we can say heat conduction is one dimensional, and let me say for simplicity, I mean the way that is the way most of the problems will actually, or most of the textbooks will always say this. Let's say it is along x direction only. So what we can do now is, so that would mean that d by dy and d by dz derivatives are 0. So we'll have d by dx of k dt dx plus q dot is rho cp dt dt. So the next module that we will start maybe later this week or next week, starting early next week, will actually be calculating the solutions of this equation for a variety of scenarios, the 1D heat conduction equation. Okay, so I think I've covered a lot of material for today. So we will stop here